recording right now. Thank you, Professor Venkatesh, for these seminar sessions on MEMS technology. We are in the last seminar session about fundamentals of microfabrication, the fabrication process flow, and characterization of MEMS. So please, Professor Venkatesh, it's time to begin.
Thank you, Carlos, for your introduction. Okay, hope my screen is visible. Okay, good morning, good afternoon, good evening, based on the wherever you are. Now, in the today's session, we are going to cover on the microfabrication and characterization. In the previous three webinars, we had already covered on the design sector. Now we shall go on to the next phase, that is on the fabrication. So if you look at the process value chain under consideration, the first and the fundamental thing what comes out will be a design. So whenever you take up any of the electromechanical system, any MEMS structures under consideration, they indeed consist of proof mass suspended with the help of set of beads, or it could be just a beam itself. So we can come out with the design already. Suman has taken you through a session on console multiphysics as well, wherein he has given us a flavor of how you can design the structures in console and also how you can even interface with the MATLAB. All those things have been covered. The detailed coupled field simulation has been carried out by all of you. All of you might have got a flavor of how to do the design of the microstructures by now. Now, the next phase, let us say design is there in your mind. The next phase is to fabricate the structures. So once we fabricate the structures, either we can go with the 6-inch wafer, 4-inch wafer, right? And we can fabricate the structures. And then here you can see we have a 6-inch wafer, which is there in my hand. I'm going to dice each one of them and I will singulate the individual structures. That is basically a dicing process. And after the dicing process, I will further die attach to the substrate and I will do the wire bonding. And then after the wire bonding, depending upon the application, I may even go forward for the hermetic sealing. The one of them, what you can see is an ADXL accelerometer, right? So basically another one is an ADXL analog devices gyroscope under consideration. So these are the packaging considerations. So whenever you look at the process value chain here, so here you can see that we do have the packaging itself, right? So majority of the cost will go with the packaging. So it's always recommended that before going to the packaging, you do all the testing for your microstructures and see whether it is really meeting your expectation or not, right? So that is very much important. That's why the characterization do come into picture. First, we will start with the fabrication and then we will go forward for the characterization session. So whenever we look at the fabrication techniques, so in the micro fabrication, we can broadly classify into four things. One is the, let's say that taking up a simple example, like let us say you wanted to build your house, right? So in such cases, you will first and the fundamental thing what you do is that you will prepare the layout for your house, right? So at so and so floor, you want to have so and so things for your house. So similarly, whenever we do the micro fabrication, the first and the fundamental thing what we do is the layout generation. So for each and individual process, we do create layouts, and there are several techniques available for the microfabrication. The first and the fundamental process over there is a lithography process. Lithography process is like your Xerox machine, right? In case of a Xerox machine, what we basically do is we will basically transfer whatever is there in the master onto the another one, right? So similarly, we do even in a lithography process. We will go into the details of each one of them. And then after the lithography, let us say you have transferred the pattern onto your substrate, then we can do the additive process like your oxidation, CVD, PVD, CVD corresponds to chemical vapor deposition, PVD corresponds to physical vapor deposition. So these are all additive process. And similarly, let's say I wanted to take away the unwanted material out from the structure. So that is basically a subtractive process wherein we basically do the etching under consideration. The etching can be done either by the means of wet etching or by the means of dry etching, right? And let us say that I have a single crystal silicon. I want to improve the electrical properties of it. So I can even well do the property modification using the several microfabrication process such as diffusion and ion implantations under consideration. So first and the fundamental thing what I told over here is a lithography. So what is a lithography process? So if you look at the lithography step, first and the fundamental thing is you start the silicon wafer and then we'll deposit a thin film on top of the silicon and then we basically spin coat the photoresist, right? After spin coating the photoresist, now we are going to align the mask and we will do the soft baking, right? So this is the photo mask what I have. I will basically align this photo mask. Then I'll expose it to a UV light. Then after exposure, then I'm going to develop it, right? So after the development, so all the unexposed regions will be retained and all the exposed regions will be washed away, right? So after that, we will do the etching, right? So these portions will remain, and then the all the you can see that these portions of the thin film has been etched away over here, right? And after that, we will basically strip away the photoresist, and we will basically get a thin film on top of the structure. So we can pattern the thin film to whatever the shape you want, depending upon whatever you have it in your photo mask. I will show you some of the examples in the coming slides. So, in the photolithography process, how exactly does it work? Take a look at this. So here I am basically having a silicon oxide. I am basically putting up on top of the silicon, right? Basically, whenever you do the fabrication, you need to do it in a clean room because all the things we are basically looking at it in a nanoscale structures. If you do it in a bare environmental conditions, it's going to damage, it's going to spoil your structures. Now we have the photo mask. Now I am exposing it with this. You can see this whenever you have a negative photo mask, you now the unexposed regions are washed away and the exposed regions are retained. Now I am going to etch it in the silicon SiO2. Now you can see that. Now I'm going to ash it. Step 6. After the ashing, I can do the ion implantation or deposition first to do the property modification. And finally, I can come out with any of the structures under consideration. So whenever we take a photolithography process under consideration, we can classify them into positive photoresist and negative photoresist. Because whenever you look at photolithography process, we will basically spin coat the photoresist and we will develop it, right? So the photoresist can be classified into a positive photoresist and a negative photoresist. So first one is what we have it here. It's a positive photoresist. As you can see, that here we have this. So in case we have positive photoresist, where here we have basically a radiation which is coming out. So this radiation will basically fall on these portions of my structure, right? So basically the exposed portions of this developer will basically get loosened out and will get basically washed away. On the other hand, if it's a negative photoresist, it's going to further strengthen the exposed regions. So the exposed regions will be retained if it is a negative photoresist. On the other hand, if it's a positive photoresist, the exposed regions will be washed away. Okay, this printing technique can be basically classified into three things. One is by contact printing, other one is by proximity printing, and third one is by the projection printing. As the name itself says, the contact printing, which means to say that, let us say that I have a wafer under consideration. I wanted to transfer the mask onto the wafer. You can see that the mask is in direct contact with the wafer. That is basically a contact printing under consideration, right? Now, on the other hand, sorry, not the wafer, I should say the photoresist. On the other hand, you can say a proximity printing, there is a small proximity. There is, you can see that there is a small space has been kept away. That's basically kept away from the wafer, but a small space has been pricked. That's basically it is kept at a small proximity to the wafer, and then basically it has been the pattern has been transferred onto the structure. On the other hand, in case of projection printing, what we have is a lens system, right? We have the first lens, and then it basically next falls onto the mask. We do have the second lens, and again it will falls onto the structure. Basically, it's like a projector. It will project whatever is there on. So basically, depending upon how you are basically developing it, the printing technique can be classified into contact, proximity, and projection printing. So in case of a deposition, either you can go by the chemical vapor deposition or the physical vapor deposition or even the atomic layer deposition as well. So even let us say that if at all you want to go in a atomic layer deposition, you could even well control it at the single atomic level. On the other hand, if you want to go to the CVD or the chemical vapor deposition, we do have a CVD chamber and we can push in that. And depending upon the operating pressure, we can classify them into low pressure CVD, atmospheric pressure CVD. If you are making use of the plasma environment, we can even have the PECVD, that's the plasma enhanced CVD. So, wherein you can see in this, we have basically a gas inlet, right? So the molecules, the precursor molecules, the mass transport of the reactants will happen. So the thin film, the reactions will take place and thin film gets deposited on top of the structure. And all the unwanted things of them are basically now absorbed because the surface diffusion, right? Now, now the surface reactions will take place and the desired products will be pumped out. And this is one of the fixed beam, what we can even well realize using the CVD process. And that is a case of a deposition. On the other hand, whenever you want to realize anything, any of the suspended structures, not just the deposition will work out. On the other hand, if it is could have been integrated circuits, the deposition would CVD would have been fine, right? Then we do even require for any of the MEMS structures under consideration, we do have a micromechanical structures associated with it. So we need to go forward for the etching process. The etching process can be classified into dry etching and wet etching, right? So in case of wet etching, the wet etching is basically a chemical means. So we will basically can classify them into an isotropic etching and anisotropic etching. So as the name itself says, the isotropic etching, which means to say that like the etch rates are uniform across all the crystallographic directions, then it is basically called a isotropic etching. On the other hand, if the etch rates are different across the different crystallographic directions, then it is called an anisotropic etching under consideration, right? So since the etch rates are uniform across all the crystallographic directions, that's why we indeed get a circular grooves under consideration whenever we go for uh, isotropic etching. On the other hand, in case of anisotropic etching process, we indeed get a V grooves because the etch rates are different across the different crystallographic directions, right? You can see this wet etching one over here. We do take up a glass. We can have a protective layer. Now we will pattern that, right? Now we will put it in acid bath. You can see that the glass will basically dissolve, right? So this is basically a case of an isotropic etching under consideration. Now similarly, if you take a silicon and you put it on a KOH solution, you can see that we indeed get a V grooves under consideration. That also you can easily see, right? On the other hand, if you take up a dry etching process, for example, this is a case of a DRIE process or a Bosch process, what we basically do is that we will first start with a silicon, and we will deposit the photoresist, and we will open up a window in a photoresist, and we will do a small etching, and then we will deposit the passivating film, and then again we will basically opens up a edge cavity, again you etch it, and then you again passivate edge, passivate edge, passivate. So whenever you want to have a deep grooves in the structures and you keep on repeating the process, so that is basically what we want to call the past process under consideration. On the other hand, that was a case with a bulk micromachining. So whenever you want to realize the structures, either you can realize it with the help of surface micromachining or with a bulk micromachining. So in case of surface micromachining, as the name itself says, surface, right? So all the modifications, you will do it on top of the surface, right? So that's why it's called a surface micromachining under consideration. So you start with the silicon wafer, and you can deposit the oxide, right? And you can even deposit the polysilicon, right? So now you want to pattern this polysilicon. How do we do that? So for which you deposit the photoresist, spin coat the photoresist. After spin coating the photoresist, we need to etch it, and then right now we spin coat the photoresist and we will expose it, and then you do the etching, and after the etching process we will do the strip away the photoresist, so we will get a suspended structures under consideration, right? So right, and then you release this, then you will basically get a suspended structure. So similarly, if you want to just basically draw the same thing for a fabrication of a simple cantilever, what we can do is that we can start with a silicon, we can deposit the oxide, right? So I'll start with a silicon. Now I'm going to deposit an oxide on top of this, right? Now what I will do is that how I'm going to pattern the oxide. Let us say I will pattern the oxide. I will pattern the oxide. This is my silicon, and this is my oxide layer. Now I have patterned the oxide. Now I'm going to deposit a polysilicon over here. I'll do the conformal deposition of the polysilicon. This is basically a polysilicon layer. Now you strip away the oxide layer, right? You dissolve the oxide layer. That is basically the release process. So once you release the process, then you can, what you see is that we do have the we do get an anchored cantilever like this. So majority of you might have seen that cantilever is one end is fixed, other end is free, right? So whenever you realize the micro machined structures using the surface micro machining, note that we will always get an anchor over here. That is why it is also called an anchored cantilever under consideration. So typically, whenever we do the design, we usually take 3EI divided by L cube to be the stiffness. On the other hand, this anchor indeed will reduce the stiffness of the overall stiffness of your cantilever. So you need to design it carefully. So depending upon the oxide layer thickness, your anchor, the dimensions of the anchor will also change. But typically, in case of the any of the surface micromachining process, this oxide layer will be typically around 1 micrometer in the consideration. So the typical dimensions of this anchor length will be around 1 microns. On the other hand, my beam will be around hundreds of micrometers. So still, you can have a first order approximation of this with 3 by L cube for the cantilever. This is the first order approximation what you could have. But if you want to have a exact value of the stiffness, you can even well formulate and get the. If you are interested, you can always come back to me. We can have a separate discussion on it. So this is basically in case of a surface micromachining. I showed you here how to fabricate a simple cantilever under consideration. The same thing you can do it for any of the complicated structures also. And this is basically a case of an analog devices accelerometer, which has been realized using the surface micrometry process. These are basically a cum drives, whatever was there in case of analog devices accelerometer. So that was the case with the bulk mic. So that was the case with the surface micrometry. The other process is by the bulk etching process or the bulk micrometry. As the name itself says, bulk. So it is like I am having the bulk material with me and I want to remove the unwanted material out from this. That is basically a bulk micrometry, which can be classified into an isotropic and anisotropic etching. In case of isotropic etching, the etch rates are same across all the crystallographic directions. So usually we do even get a circular grooves in case of the isotropic etching. If you say that if L is the length and W is the width of opening, then we indeed one can derive that L to be equals to this W plus 2D. You can see that here to here is D, here to here is D. The length of this will come out to be W plus 2D. On the other hand, in case of anisotropic etching, we do always get weak grooves under consideration. This angle between the two crystallographic planes, which is basically 100 and 111 planes, will be indeed always be 54.75 degrees. Right now, you keep on, let us say, if you are dipping in a KOH solution for a long time, then it can even well lead to a self-terminate structures like this, right? So, whenever you want to realize, for example, a pressure sensor under consideration, what you can do is that you can start with the SOI wafer. SOI basically corresponds to silicon on insulator wafer, right? And you start with a silicon wafer. What you do is that you basically protect the top layer of the silicon here, and you open up a small window. You deposit the photoresist and you open up a small window over here and you start etching at it from the back side. Once you start to etch it from the back side, then it is going to eat away the silicon, right? That's what you can basically see this. I am basically opened up a window from the back side, then it will start to eat away the silicon from the back side and it will basically leaves me with a thin layer of this top one is basically a silicon, and this is basically an oxide, and this is again a silicon under consideration. This is basically a silicon, which is basically sitting on top of an insulator. That's why it's also called a silicon on insulator. Now, as we know that the etch rate of oxide is very, very small in comparison to silicon. That's why it will terminate whenever it looks at the oxide here. On the other hand, let us say that I do. Usually the SOI wafers are quite expensive. So let's say I wanted to realize the same thing with just a silicon for consideration. What you can do is that you can even dope the top surface of the silicon with boron doping, right? Whenever you do the boron doping, then you dope it with the boron, then you start to etch it from the backside. So usually it will reduce the etch rates quite extensively whenever you boron is basically etched off. It will stop the etching whenever it looks at this boron one. So you will just basically get a thin layer of this pressure sensor under consideration. So whenever there is a pressure coming up from the backside, you can actually leads to a deflection of this, which will indeed lead to the stresses inside. The stresses can be converted to the resistance change, and we can have the piezoelectric, not piezoelectric, piezoresistive readout in this. And these are the cases of in HRC, which is basically hemispherical resonator gyroscope, realized using the bulk micro machine. Now, there are several things you can even well realize. For example, if you look at the pressure sensor I told you just now, whenever there is an input pressure, we get the stresses gets induced, the deformation will be there. The deformation leads to the stresses. The stresses can be will gets converted to change in resistance. That process is basically called the piezoresistivity, right? Piezoresistivity. Because of the piezoresistive effect, we indeed get the change in resistance. This change in resistance, if we connect all the resistors in a V-Stone bridge configuration, we will basically get a voltage output. That was the basic principle of the pressure sensor. Now, on the other hand, all of us are using microphones on day-to-day basis, right? So, what is the basic fabrication process followed for the fabrication of a MEMS microphone under consideration? First, we will start with a silicon wafer and we will deposit the nitride on the top and bottom, right? And we will deposit the polysilicon. So in the earlier case, where you can make use of oxide or the nitride, both will basically be the same. So we have they will deposit the polysilicon, and then on top of that, I am going to now deposit the oxide layer. I'll do the conformal deposition of the oxide. I did the deposit of polysilicon and I patterned the polysilicon for the first, and then now I am going to deposit the oxide, right? Now I have this oxide. Now what I will do is that I can deposit the metal layer on top of it. This will be a gold or aluminum. Next, I have basically etch away the things over here on the metal layer. You can see that I did the perforations on the metal layer. So let's say that on top of that, now we can even well deposit the silicon nitride again. Now, let us say that once I deposit the silicon nitride, now I will start etching it from the back side, right? I will basically create a etch window and I will start to etch from the back side. Now, what I have with me is that I have basically have the silicon nitride over here. I'm going to strip away this nitride layer also, and I'm going to strip away this oxide layer as well. Now, what I am left with will be this bottom electrode and the top electrode, right? So whenever there is an acoustic input coming onto the structure, which indeed will lead to the deflection of the diaphragm, this deflection of the diaphragm will be sensed by the capacitance change between the pressure sensors can be basically packaged by several means. One can do the complete vacuum packaging, which will actually measure the absolute pressure under consideration, or you can package it at a desired known pressure. Then whatever you will basically get, let's say if this input pressure P is coming up, you will basically get P minus P naught will be the whatever is the output you will be getting out will be based on this. On the other hand, we can even well have a window from the bottom side. Let us see that from this side, I have some pressure PA. From the top, I have another pressure PB, let us say. Then this can measure this delta P, which will be a difference between PA minus PB. The differential pressure sensing can be done depending upon the packaging strategy, whatever you are going to follow. Now, on the other hand, in case of whenever you want to, you look at it in any of the automotive industries or anywhere, the accelerometers and gyros plays a very, very critical role. So, to start, for accelerometers, since there are inertial sensors, we indeed require a larger proof bus under consideration. So, for the larger proof bus, it's not recommended to go with the surface microvision. So whenever we go with the surface micromachining process, we will always left with a thin layer of the structure under consideration, right? Usually the structural layer thickness will be around 2 by cross, 3 by cross under consideration. So typically in case of an inertial sensor, since the inertia plays a very, very important role, so it is always recommended to go with in bulk micromachining process or the SOI process under consideration. So in case for the SOI process, we will start with the SOI wafer. This is basically silicon. This is a handle wafer. We have the oxide layer and we have a device layer. So this is basically SOI wafer. And then I will do the first lithography process on this. Now I am going to pattern the approach. See what exactly is there in that lithography process. Wherein I will basically have the silicon. I'll deposit the thin film. I'll spin coat the photoresist. Right? Now I am going to align and mask it. This is a photo mask, what it comes out. Whenever I am going to expose it to the UV light, then expose, I'll do the hard baking and I'm going to develop it. And I'm going to etch away the unwanted things. So then this is basically my photolithography process. This we have discussed in detail already, right? So after the first lithography process, we have now did the electrode deposition using the first lithography. In the second one, now we will do the second lithography process, wherein after the second lithography process, we will basically open up the windows for etching the structure, wherein I will basically do the silicon DRIE process. Typically, this device layer thickness in this case will be around 25 micrometers under consideration. We need to have a larger, the deep etching of the structure. So we need to go forward for DRIE process, which corresponds to deep reactive ion etching process, right? And let us say that after the deep reactive ion etching, we need to release this somehow, right? We need to suspend it. So as to release it, we will basically do the what we will you will basically now do the next litho. We will basically do the litho from the back side, and then we will do the back etching of the silicon. This is the pressure sensor, what has been packaged. You can see this. And this is the one which has been used even by the Bosch as well. The basic working principle of this is this is basically a sensor and this is a signal processing circuit. This is a sensor basically. I told you that it's basically a piezo resistive base. So whenever there is an input pressure, then there will be a change in resistance. Then now they are connected in a V-Stone bridge configuration. Change in pressure leads to change in resistivity, which leads to change in resistance, right? Whenever there is an input pressure, you can see that there is a change in the voltage, which basically comes out from the V-Stone bridge. So this is the basic heart of this Bosch pressure sensor under consideration. On the other hand, in case an accelerometer also, wherein we have the proof mass suspended with the help of set of beams, and whenever there is an input acceleration coming onto this, then what happens? It leads to the deflection of the proof mass, which will lead to what? The change in capacitance between the comb fingers under consideration, right? So that's how it's basically sensing the acceleration. So look at basically the working principle of the accelerometer and the process behind it. So, right here, the accelerometers are almost everywhere nowadays, starting from your mobiles to even in wearable electronics, everywhere it is there. It has a signal processing chip and an accelerometer. Accelerometer basically consists of what? Your proof mass suspended a set of beams, and we have a comb drive resonators, which basically sense the change in capacitance, right? Depending upon acceleration or deceleration, there's a change in the capacitance that you can see there. Now that capacitance change is now converted into the voltage output by connecting it to the ASIC. ASIC basically corresponds to application-specific integrated circuit, which basically converts this change in capacitance to the voltage output, which is proportional to the what is input acceleration coming on the structure. And the next one is the gyro, that is the case HRG or a heavy spherical resonator gyroscope. The HRGs plays a very, very important role in majority of the whenever you want to go to the inertial grade sensors, this HRGs plays a very, very important role. So in majority of the defense applications, this HRGs play a extremely important role, right? In this case, since this is a completely spherical structure, we do have a perfect match between the drive and sense modes of the gyroscope. For any gyro to be in operation, the first and the fundamental thing is that there should be matching the tuning the frequencies between the drive and sense directions, right? And there should be a perfect match with the drive and sense mode, and also the decoupling of both the modes are equally important. So decoupling and the frequency tuning plays a very, very important role in case of a gyro. So since it is a heavy spherical structure, it's a spherical structure, so what happens? We do get the degenerate modes. Since we have the degenerate modes, this indeed will improve the sensitivity tremendously for this, right? So this is the basically a working principle of the what is there in the Bosch gyro. Look into it. This is basically inertial sensor. What is there? It basically measures the what's the turning angle for the vehicle under consideration. Wherein in this case I had the accelerometer and the gyroscope together. That basically comes gives us to the IMU, which is basically inertial measurement unit. We have basically a proof mass suspended with the help of set of beams, right? Whenever it's basically rotates, then it gives us the Coriolis force, which will basically lead to. So these are basically operated in the anti-parallel mode of vibration. That is basically a drive mode. When there is input angular rate, then it will start to vibrate in the sense direction, which leads to capacitance change in the sense direction. This capacitance change is proportional to the speed of rotation. You can see this, right? When you, right? And these MEMS are not just in the commercial applications. Even in several medical applications, they play a very, very important role. For example, these are all even on the cardiac devices, even on pacemakers, even on the lab on chip, organ on chip, plenty of applications are there for this. Look at this. Here I have basically a MEMS device. Look at what it does. It is basically sending us the signals. See what it does. So whenever there was a blood clot, so what the MEMS device, it is basically even it could be helpful for the healing purpose as well. Now, what is the process that we will be following for fabrication of the devices in our case, right? That is what is basically called the SOI process. The earlier it was called a SOI MEMS process, which was now taken up by the science foundry. So this is now called the SOI process from the science foundry. Okay. Now, what is the basic process flow in net? So the basic process flow follow in the SOI MEMS process or the SOI process in the science foundries as follows. So we will basically start with an SOI wafer. This is my silicon. This is my oxide. Right? And this is my, again my silicon. That's what you can see here, right? These are the color codes, what you can clearly see. This is a silicon, this is my buried oxide, and this is the substrate, right? Now, I am going to deposit the top layer I'm going to dope it with PSG so as to, because silicon as it is may not have such a good conductivity, so as to improve the conductivity I'm going to now deposit the PSG. Now I am going to strip that PSG now. Now what I'm after the doping that, now I'm going to coat the photoresist, spin coat the photoresist. After spin coating the photoresist, now I need to pattern the photoresist, right? Now I will basically use the first mask, and now I am going to pattern the photoresist with the help of the mask. Now, after patterning the photoresist, now we are basically now going to deposit the pad metal, right? Now I'm going to deposit the pad metal. You can see that the pad metal gets deposited over the top layer as well as on the silicon also, right? It will just, it will get deposited on the top. It will get deposited on the top as well as on the silicon as well. Now, after that, what we'll do is that we will lift off the metal from the top layer. And now we will be left with just the pad metal which is there on the silicon, right? Now, after this, what we do is that we will strip away the photoresist. We will dissolve the photoresist. We will dissolve the photoresist. Next, after dissolving the photoresist, we are left with this, right? We just have a pad metal on top of the silicon. Now we need to now further do the processing of this structural layer also, for which we need to again do the next set of the photolithography process, for which again you deposit the photoresist, right? Next, after depositing the photoresist, as I said, we need to pattern my SOI layer. I need to pattern my structural layer, right? So make use of the SOI mask and then start patterning the photoresist. Make use of the SOI mask and you pattern the photoresist. Now, after you pattern the photoresist, now you have opened up the windows over here. And then now, since this structural layer thickness for this is now usually 25 micrometers, that's a fixed thickness. Don't go for any other values during your design. You stick on to 25 micrometers for the structural layer thickness. And then now you can see that since the thickness is quite large, I need to go forward for deep reactive ion etching. Now I will do the DRIE process. Now I will get the deep cavities on the structure. Now after the DRIE, now I need to strip away this photoresist also, right? Now I am left with this metal, sorry, this is my pad metal, and this is my patterned structure or the patterned part. And I have this oxide, and I have the buried oxide as well as my substrate with me. Correct? And the bottom oxide is there. Why do we keep the bottom oxide? Because even I don't want this to be etched away during the same process. Right? That's why indeed I deposited the oxide layer over here. Now, now next is that after this photoresist, stripping away the photoresist, now you protect the top. Now you protect the top layer. Hope you guys are following. After I have stripped away the photoresist from here, I stripped away the photoresist after the DRIE process. Now I am going to protect the top surface by the deposition of the polywhite layer on the top, right? Now what I will do, I will now do the photoresist deposition at the bottom, right? Now I am going to pattern it from the bottom side. Right? You have the oxide. Now you pattern it from the bottom side. You can see that I had deposited a photoresist and I start to pattern it from the back side. Using what? Using my trench mask. Right? Now you etch the bottom oxide first. First you etch the bottom oxide. That will be usually done using a reactive ion etching process. Now, after the reactive ion etching, now we have this window Now we have protected the top structural layer. Now you etch you etch it from the bottom. You do the deep reactive ion etching. You do the deep reactive ion etching. So you will basically get a cavities like this, right? Now after this, as since we can see that whenever we do the DRE, we do always get this flows out over here, and sometimes we even go to even do the undercutting as well. Now we have basically what we have this photoresist with me. We have the bottom oxide, and then I have the substrate material along with me. Now we have what we have basically patterned the substrate that guides the and gets the buried oxide layer. This is basically done using the wet etching process. Next, you can see that now I even have on top of this what I have a polyimide layer. I have to take away the polyimide layer. So that's what I am doing here. I am stripping away the polyimide layer from the top, right? Now, once I strip away the polyimide layer, still I am left with this oxide and the photoresist. The first and the fundamental thing is that you first strip away the photoresist. You chemically strip away the photoresist. Now I am still left with the oxide. Now you remove that oxide layer also, wherein you can basically expose it to the wafer HF. Then you can remove the oxide as well. Now you will basically left with what you will be left out with just a structures like this, right? So you can see that I had the oxide here as well. I have the oxide here as well. So both of them will get stripped away whenever I'm going to expose it to HF solution, because HF will enter it from the top as well as it will enter it from the bottom. So it will do the undercutting, and also it will etch away the complete uh, oxide layer over here. So we can even well get the electrical contacts. Let us see that in case of if you want to realize the structures for the capacitive sensing. Here I have a contact for the top electrode, right? But I wanted to have a electrode at the bottom, for which you can make use of this. Okay, we have another metal layer. You can see this. We don't have just the pad metal. Pad metal sits on top of the structure, but this blanket metal can actually give us another contact, which is to the bottom silicon under consideration, right? If at all you want to have another electrical contact for the bottom silicon, you can indeed deposit a blanket metal layer under consideration, right? So these are the dimensions of the different layers. The silicon layer, the structural layer is 25 micrometers. The substrate is 400 micrometers. Buried oxide is 2 micrometers, whereas the blanket metal is 0.65 micrometers. The thickness I am talking about, and the pad metal is 0.5 micrometers, right? And this same thing has been tabulated over here. And these would be the some of the variations what we could expect during the fabrication, right? And these are the resistance values for the each and individual layers under consideration. I hope this is clear, guys. I hope it's clear. This is the basic process what we will be following for the fabrication of your devices. So whatever the designs you are doing, please stick on to these dimensions. Please don't change the dimensions. You have to stick on to these dimensions. And whenever you want to carry out the electrical simulations or mechanical simulations, keep these properties in mind during your design phase. And whenever we submit the designs, we indeed will go through series of design rule checks. So what are those DRCs, the design rule checks? So let us see that we have fabricated the structure. So this is my blanket metal, which is there on the bottom silicon, and this is on the structural layer, correct? This is on the substrate, this is on the structural layer. And this is basically a pad metal, this is my blanket metal, this is a silica, and this is my substrate. This is a buried oxide which is there between the two. The first and the fundamental thing in the design rule check is, let us say, this is for the pad metal layer. So if you look at the, whenever you want to do the layout for this, we do come across these different layers. One is a pad metal layer, another one blanket metal layer, next one is the silicon layer, next one is a buried oxide layer, and the last one is a substrate layer, right? So let us go one by one. What are the design rule checks you need to follow for each and individual layers under consideration? The first one is for the pad metal. For the pad metal, we need to ensure that if at all you have a pad metal over here, this is the edge of the pad metal, this is the edge of the pad metal. The pad metal layer is not accidentally exposed to the SOI basket, right? Let us say that whenever it does the under etching, this pad metal should not get etched away. So we need to ensure that a minimum 3 micrometer gap will be left between this edge and the edge of the pad metal. This is the first constraint which need to be kept in mind. Whenever you are doing the layouting, keep this in mind. The edge of this structural layer and the edge of the pad metal, the minimum 3 micrometer distance has to be maintained. Next one is for, right? Now, we have this pad metal with me, right? Now, this is my trench layer. Wherever you can see, this is basically the trench layer. So this is the edge of the trench layer, let us say. So from this edge of the trench layer, from one to the other, there should not be maximum what you can, sorry, minimum what you need to leave will be 50 micrometers. This is the minimum distance what you need from edge to edge. Should not be less than 50 micrometers. And the third one is, let us say this is the edge of this, right? And then this to here, this minimum distance minimum should be 10 micrometer. This basically, by considering the second rule, that ensures that the silicon is anchored to the substrate quite carefully, right? It should be clearly anchored to the substrate. It should not be hanging, right? That's very much important. And the fourth rule, come on, fourth rule, that's the rule D. This guideline will basically ensure that the silicon structure is released from the substrate layer. What is that? We need to, whenever you are having the holes, right? Because the etchant can enter into the holes and this oxide layer can be easily etched away. So that as to see to that, my silicon can be easily etched away. You can keep what you are whenever you are, if at all you are having your holes, you can keep the hole dimensions to be around 5 micrometers under consideration. The minimum future size you can keep it for the structural layer to be 5 micrometers. Now, on the other hand, if at all you have a blanket metal layer, if at all you have a blanket metal layer, this is my blanket metal layer, this is the central line of the blanket metal layer, you need to leave across 35 micrometers alongside, there should not be anything. So if you need to have minimum 35 micrometers, there should not be anything. Across the blanket metal layer, we need to leave a tolerance of 35 micrometers for the blanket layer. So whenever you are doing a layouting in any of the layout preparing softwares like a key layout, Calidate, Clavin, or any other softwares, these are basically the different layers what we have come up. One is the pad metal, another one is the SOI, and then the other was the SOI4. SOI4 will be usually used whenever you have the perforated structures under consideration. And we do get a trench layer, where that's basically wherever we want to have completely suspended structures, you basically make use of the trench. And the blanket metal, will basically come on the bottom silicon, right? That's basically for the substrate. So whenever you make up the layouts, in the each and individual mask, there is a number. These are the numbers for each and every mask. The pad metal will be having a mask number of 5, and SY will be having a mask number of 10. The mask number you need to define it carefully during your layout editor. And the minimum future size for each one of them are as follows. 3 micrometers for the pad metal, 3 micrometers in the for the SOI hole, and the trench should be around 200 micrometers. That's the minimum future size, please. And then blanket metal, the minimum future size is 100 micrometers. That's the minimum what you need to keep. And the minimum spacing in case of pad metal is 3 micrometers. And then in case of SOI, it should be 3 micrometers. These are the DRCs you need to keep in mind. And whenever you are making use of SOI MEMS process, in case now it has become the science binary SOI process, so you should not get more than 33% of the overall area. That is one of the constraints what they basically give us, right? And the trench should not cross basically 25% of your entire area. And the blanket metal should not be more than 20 micrometers square under consideration. Now, what and all is really required and what is not so? What is a real constraint and which is not? First one is that the SOI encloses the pad metal. The minimum dimension should be 3 micrometers. That's a mandatory thing. This rule ensures that the pad metal layer will not be exposed to the SOI mask, because we know that there will be even the under etching also, which comes up, right? That's what we basically told here for the 3 micrometer. This has to be maintained. This is mandatory. This is a mandatory condition. Please don't forget this. Then the trench, it is not a mandatory condition, but it is recommended, right? And I discussed all of them, right? So SOI future size, these are the basic functionality for each one of them. SOI trench space, this guideline basically ensures that the edge of the substrate does not undermine the edge of the silicon, so that during the trench etching process under consideration. And SOI future size should be at least 10 micrometers, not a mandatory condition. Even we have realized the structures which are even 5 micrometers also, right? That's not a mandatory condition. And the trench encloses a silicon structure, which is 5 micrometer, that is not a mandatory condition. The guideline is provided so as to ensure that the silicon structure is released properly, right? But it is not a mandatory constraint, right? Even you can have completely rigid structures and still you can get it out. Completely unperforated structures and still you can have it. And blanket metal alignment of 35 micrometers, that's not mandatory constraint. The mandatory constraint is this. Please keep this in mind. This is a mandatory constraint, and remaining of them from B to F, these are all the recommended constraints under consideration. So please keep these DRCs whenever you are preparing your layouts under consideration. So what are the design standards? So usually the chip size will be 11 mm by 11 mm, wherein your design area will be 9 mm by 9 mm. But what has been given for you, the suggested limit is 8.5 millimeters by 8.5 millimeters. Now, for the blanket metal, right, what is acceptable, what is not acceptable? So the acceptable layout for the blanket metal is this, right? So if you hash it here clearly, then it should be able to hash it. On the other hand, if you have the blanket metal or the trench mask layout like this, then there are more chances that the structures will completely fall off, right? So you can't have a donut structures like this, either in the blanket metal or in the trench mask. And then whenever we do, in case of the SOI MEMS process or the MEMS process, we indeed go forward for the subdicing. So during the subdicing, we need to ensure that from this edge to a structure at minimum 500 micrometer gap should be maintained. Then for so as to ensure that we get a better anchor alignment, the structures are properly anchored, you can either do the filleting or you can even well provide the anchors like this, right? You can give a 45-degree lines and then you can provide the anchors. But if you just lay up the straight lines, there are more chances that it will not sustain the anchor. The anchors will not come out properly. Now, if you look at this case, you can see that one contact is here, another contact is here. Whenever I apply a potential between the two, then it will indeed will undergo short circuit will be there. So there will thus no electrical isolation in this case. On the other hand, whenever we want to ensure that whenever you do the design, you keep in mind this electrical isolation. You need to, whenever you are keeping the pad metal, ensure this electrical isolation. And in your software, whether you're using K-Layout, Clavin, anything, don't go forward for structures like this, right? So if you at all you want to have structures like this, you can make up the structures, or it should be a closed structures, and you should be able to hash it clearly, right? If you do the B hash, you can easily hash it. And these are some of the devices what we had realized using the SOI process. This is basically a case of an electrothermal actuator what I had realized at Indian Institute of Science. And this was a case of a microphone, and this was a case of a gyroscope. And there are plenty of other things which I had realized. For example, the accelerometers, even a triaxis gyro, one we do have the MEMS microphones and speakers, plenty of things were there on this slide. Okay, I'm just showing up the three of them over here. Okay, now I hope the things from the fabrication side is fine. Which one do I have? Now, coming to the next one, let us say that you have the fabricated devices with you. You will prepare the layout and you will get the things fabricated. Now you need to characterize it somehow. You need to see to that whether they are meeting my expectation or not, right? For which you have to do the characterization. In case of characterization of the MEMS devices, as the MEMS devices are basically what? In electromechanical structures, right? Wherein we need to go forward for the electrical characterization, and also we need to go forward for the mechanical characterization. So I will discuss in detail about the characterization of my process. Right? So whenever we look at the system development under consideration, right, we do come across the design phase, fabrication phase, characterization phase, and then the packaging phase. Now we are looking into the characterization phase. So whenever we look at the MEMS devices, they can be broadly classified into the static MEMS devices and the dynamic MEMS devices, right? So that's a broad category what I'm talking about. And whenever you take up your dynamic MEMS devices under consideration, so what is the hell? Where do we need to look into the dynamic characteristics of it? And how to measure the dynamic characteristics, and what are the, if at all we can measure it, where we have to actuate it somehow, and then after the actuation we have to measure it also. So how to actuate, how to measure, and what is the experimental setup we need to follow? Let us discuss it in detail. So in the design development, the fabrication, characterization, this I had discussed. Now, now we have discussed on the fabrication, we have discussed on the design. Now, in case of characterization, one can do the wafer level characterization, or you can even do the system level characterization. Whenever you fabricate the devices, for example, we have seen in case of fabrication that we will take up the single crystal silicon and we will deposit the oxide and we will pattern the oxide and we will deposit the polysilicon on top of this, right? So that is for a case of a simple cantilever beam, what I am speaking to, right? Now, let us say that while stripping away the oxide layer, now let us say that my oxide is still sitting away at some points. My oxide is still sitting at some of the points, somewhere over here, here, it has not etched away completely. Then what happens? My structure is completely stuck at this position, because whenever we come down to the micro scale, you know that surface effects will overtake the volumetric effects, correct? Since the surface effects overtake the volumetric effect, so surface tension is actually a surface effect. So there are water molecules over here that because of the surface tension, so what would happen? The top electrode will actually come and stick onto the bottom electrode. So that is basically a problem of stiction, and that is basically during since there is no release of the oxide layer, we need to see to that the first and the fundamental thing, whether my structures are released or not. Right? That's the first and the fundamental thing. If at all we are going forward for the packaging, if the structures are not released, then the industry is in an utter loss, right? And then one can look at it from one can measure the dynamic performance characteristics and also the static characteristics as well, right? In case of dynamic characteristics, what and all we can measure, and after the measuring the dynamic characteristics, what and all we can evaluate it from there, right? And it's not only from the wafer level, that's in the wafer level characterization. And then once we package, once we, let's say that what I can given will connect it to the readout circuitry, and we can do the system level characterization also, where in case of system level characterization, we can go to measuring the sensitivity, all the performance characteristics of your sensor under consideration. And then whenever we do the characterization, we do see to the, we expect something and what it comes out will be something else. Then there could be chances that we can even see what are the post-fabrication effects on your sensor, how it's going to affect the performance of the sensor. It is going to really deteriorating the performance, or it is enhancing the performance. We can see from the post-fabrication effects. That's what you can even realize during the characterization process. Right? So after the wafer level characterization, you can go forward for the packaging and then take it to the real use, wherever you want to use it. Now, whenever you take up a dynamic characteristics, the dynamic characteristics, for example, if you take up any of the dynamic MEMS devices, what comes out to the first and the fundamental thing, what comes out will be the resonant frequency and damping will dictate the performance characteristics of the dynamic MEMS devices, right? So consider a MEMS gyroscope. So what is there in case of a MEMS gyroscope? It consists of a proof mass suspended with the help of set of beams, which is driven with the help of a drive circuit. So it starts to vibrate in the drive direction. Now, when there is an input angular rate signal, then what happens? Then there is a Coriolis force. The structure starts to vibrate in the sense direction, which is basically sensed with the help of sense circuit. Now, these are basically a governing differential equation of motion. This is in the drive direction. and this basically comes along the sense direction. And here, if you look at the plot, you can see that when there is a perfect match between the drive and sense mode frequencies, we get a large amplitude vibration in the sense direction. On the other hand, when there is a huge mismatch between the drive and sense mode frequencies, then there is a reduction in the sensitivity of your system, but there is an increase in the bandwidth, right? So there is always a trade-off between the bandwidth and sensitivity of any gyro under consideration. So you need to keep in mind whenever you are doing the design, you need to whether you require a larger sensitivity or you require a larger bandwidth. So we need to design it accordingly, right? And after the fabrication also, the lot needs to be done from the characterization side, right? So these are some of the fabricated devices. So this is basically a gyroscope with a hammock suspension. So wherein I am basically having this home drive resonators for the driving, and for sensing, I have the bottom electrode. Can you see this electrode line over here? These are basically a bottom electrode line, which is just below this, right? So this is by perforated proof bars. These are by beams which are holding the perforated proof bars. These are driven in the drive direction with the help of fingers. And whenever there is an input angular rate signal coming up along this direction, which is basically sensed with the help of capacitance change between this bottom electrode and the structure. This is another configuration wherein this is again consists of a proof mass suspended set of bits. This is driven with the help of the drive circuit by using the comb drives. And for sensing, we do have this bottom electrode line over here. Can you see this? This is basically a bottom electrode line. All right. So, which is again sensed with the help of capacitance chain between the top electrode and the bottom electrode. So, if you look at the gyro I showed you in the previous slides, we need to ensure that we do get the what your this is basically a dynamic MEMS device, and not only the gyro, even if you consider a case of an accelerometer also, the resonant frequencies indeed will dictate the range of operation of your accelerometer, right? So this natural frequencies plays a very, very important role. Now, how can we measure the dynamic performance of any of the sensors? So how can we do that? So can we go by the contact means? For example, let us say that I have the railway bogies. They are undergoing vibrations. Then you may say that I will mount the accelerometers on top of that and I will measure the vibrations. Can you do the same for the MEMS devices? Because if you take up the MEMS devices, there are suspended structures. Even if you touch from your bare hand, the pressure what you apply from your touch feeling that itself is enough to damage the structures. So it is not recommended to go with contact approach. So that is why we indeed go forward for non-contact approach, wherein you can make use of laser Doppler vibrometer or a position sensing detector. There are plenty of other things are available to measure the performance characteristics of the micro and nano systems. So what exactly is the working principle? As the name itself says, laser Doppler vibrometer, it basically makes use of Doppler effect. So what is the Doppler effect? Consider a light source. If the light source is at rest, right, and the observer is here, then what happens? Then, then what happens? We don't see any change in the wavelength, correct? Now, consider the next case. When the light source moves close to the observer, then what happens? Now, there is a change in the frequency. In this case, what happens? There is an increase in the frequency or the reduction in the wavelength, correct? So that is basically called the blow shift of the observer is at the opposite side. then there is an increase in the wavelength and reduction in the frequency. That is basically called the redshift. And this is basically what we call it as a Doppler effect. So in case of laser Doppler micrometer, as the name itself says, it makes use of laser and it uses the Doppler effect to measure the vibrations. That is why it's called a laser Doppler vibrometer. So what is the working principle of the laser Doppler vibrometer? Let us see. Okay. This is basically measuring the car vibrations. Enlightenment. Now we have a laser light, which basically falls on the interferometer. Interferometer splits into two parts. We have photodetector. One falls directly onto the photodetector. Other one falls on the incident test object. Now it basically scatters the light. That now falls. Now the back scatter. You can see that there's a change in frequency in phase of the back scattered laser light. Now both of them will combine together. Right? This is a superposition of this with the now we get a modulated detector output. Right? You can see the Doppler shift. Now there will be a signal processing unit which basically converts this change in frequency and phase to the change in velocity and displacement. That's basic working principle of the laser Doppler vibrometer. Right? Now, I hope that is clear. The laser working principle, laser Doppler vibrometer. Now, whenever we do the analysis with the laser Doppler vibrometer, the first and the fundamental thing is that what we did was we had a structure. For example, let us take a cantilever. Correct? Now we have a simple cantilever B. Now the cantilever and I have a bottom electrode considered like a MEMS structure. Correct? Now let's say that I apply a DC potential to this. Then what happens? Then there is an electric field which gets established. So it is just like I have a cantilever and I am applying a static load onto this. If I apply a static load, then it will basically undergo deflection like this. Now, instead of applying a DC signal, now what I will do is that now I am going to apply a AC signal to this. Then what happens? If I apply an AC signal, then this cantilever starts to vibrate about its equilibrium position. Correct? So once it starts to vibrate about the equilibrium position, now I want to measure the vibrations of the cantilever. For measuring the vibrations of the cantilever, I basically make use of laser Doppler vibrometer. So we know that when the cantilever undergoes vibration, what happens? We do get maximum displacement at this point and zero displacement at this point, right? So what we do is that we will discretize this entire structure into several data points. Just like whenever you do the analysis in any of the FEA software, the first and the fundamental thing what you do is what? The meshing of the structures, right? So similarly, here also I'll discretize the entire structure into several data points over here. Now, I will make the laser to fall at this position, and if I apply a single AC signal at one frequency, then the structure starts to vibrate at that frequency. Then what? I will basically get one response. Correct? Now, let us say that instead of applying just V naught sine omega t, now I applied at omega, then I got the output at omega. Now, what I will do is that I will sweep this frequency. Once I sweep the value of omega, then what happens? Then I will basically get the frequency response of the structure, correct? At different frequencies, what is the amplitude of vibration I can measure, and I can make up an envelope of it, then that will be the frequency response of my structure, correct? So now we get the frequency response at this point. I can evaluate the frequency response at this point. I can evaluate the frequency response at different each and individual data points. Each and individual data points. Each and individual data points. Now, whenever we have a frequency response like this, if you do the peak picking, the peak of this is nothing but the frequency corresponding to it is nothing but your natural frequency, correct? And if you do the take up the 3 dB points and if you drop it down, then I will basically get the bandwidth, right? I'll get the bandwidth of this. I'll get the bandwidth of the structure. Now, similarly, if I have the bandwidth, if I have the frequency, I can evaluate the quality factor, which is Fn divided by delta F, which is the bandwidth. So I will get the quality factor, which is basically dependent upon the damping present in the system, which is 1 over 2 theta. From this, you can evaluate what is the damping present in the structure. Correct? So the damping is again a mess. So depending upon the operating frequency, depending upon the operating pressure, the air medium which is there between the top electrode and the bottom electrode, air can behave as air can behave as rubber, air can behave as honey. Air has a different properties and different pressures and different speeds. Right? So now I said from this, I can evaluate the natural frequencies of the structure. Now, if I do the measurement at each and individual data points, then at each and individual frequencies, I can get I can even measure the things at each and individual data points, and I can have let us say that I will measure it at one frequency for this point, and the same one for the next one, it may come at this position, next one it may come at this position. So if I plot it as a function of x, the deflection delta as a function of x, then it will basically create the mode shape of the structure. So whenever you do the analysis with the laser Doppler vibrometer, you can extract out the natural frequencies and mode shapes quite easily. I think there was even a demonstration on the console multiphysics also on we can always do quite easily using any of the analysis softwares, the modal analysis. So if you compare between the vibrometers to whatever the readings you get out with your LDV, with any of the analysis softwares, we can see that analysis softwares, if you do the modal analysis, it's like you're extracting out the natural frequencies and the mode shapes, right? Fine. If you do take up the frequency response in case of the vibrometer, that basically is like you are carrying out a harmonic analysis in any of the FES softwares. When you carry out the harmonic analysis, it will basically use how does the structure response is there as a function of frequency, right? So on the other hand, if the same thing, if you look at it in a time domain response, then it is equivalent to doing a transient analysis in any of the commercial softwares. So what is the hardware associated with it? The hardware associated with it is as follows. So whenever we have any of the MEMS structures, we have any of the MEMS structures, MEMS sensors under consideration. So this is basically a sample, what you can see here. Sample, what you can see here. This is basically a device under test. This is basically a device under test or a sensor under test, right? And whenever you want to do the measurements with the LDV, we need to drive the system. So if at all we have the top electrode and the bottom electrode, you can even well apply the potential between the top electrode and bottom electrode, and you can drive them, right? So one need to have the driving unit for us to actuate my structure, right? So this MEMS driver can be even well, the signals can be provided with the help of the signal generator, and this MEMS driver will drive the sample or the device under test. Since they are all microstructures, we require the microscope optics to view them, correct? To view them, and and so whenever you take up a microstructures, they are all what? There will be in plane motion as well as out of plane motion. So for which we have two units. One is the out of plane unit, other one is an in plane unit. The out of plane unit, that's what you basically saw in the video, wherein we have the structure which is the laser is coming like this and the structure is vibrating in a direction orthogonal to the direction of your laser line, right? So that is my out of plane unit. The laser scanner will basically measure the out of plane unit. On the other hand, if at all there is in plane motion of the structure, then this will basically measured with the help of stroboscopic effect, wherein we basically make use of strobe LED and we will flash light and we will capture the regular images at the regular interval of the time. And of course, we do have a camera to capture the images. And this we can see that this we have a laser scanner. This indeed is connected to the vibrometer, and the strobe driver is connected to the strobe LED. Right now, all this is further now the VFI has to drive the MEMS driver. We have a signal generator within this, and then the computer will indeed control my vibrometer. Right. So what are the different parts we have? Wherein we have in vibrometer controller. The vibrometer is nothing but your laser unit, and video basically saw all the optics which is there inside this dabba. Okay, and then we have a strobe driver, we do have a signal generator, and we have a MEMS driving unit, which is basically here I have a 6-inch wafer. I basically probed it and basically applying an electrostatic actuation, and then I am measuring the response. And within the controller, we do even have what? Within this MEMS controller, we have the controller. Here is basically a controller. Within this, we do have a decoder unit. Can you see this chip over here? This is basically a decoder unit. This decoder, if you looked at the video, then what it showed you was whenever there was a motion of the structure, then what happened? There was a change in frequency and phase, right? But what we got out was change in frequency and phase. Now, this decoder will basically convert this change in frequency to the velocities and change in phase to the displacement of the structure. So that is the basic working principle of the laser Doppler spectrometer. So in case of this Polytech scanning vibrometer, we have basically the three modes. One is acquisition mode, analyzer mode, and the presentation. So just like how you have it in any of the commercial softwares, how we have pre-processor, processor, and the post-processor. Similarly, in case of the vibrometer also, we do have this acquisition, analyzer, and the presentation. So in case of an acquisition, we do acquire the geometry, that is getting the geometric model, and we will set the optics and we will define the scan points, that's like the meshing, and then we will set up the parameters. So these are all several MEMS devices which are there. and I can acquire the images of this, and I can define the scan points, and I can set the optics. By setting up the optics, we need to ensure that we get the desired reflection back from the structure. And while setting up the parameters, either you can look at things from the time domain, from the frequency domain, or you can even well look at the things from the time domain as well, right? And there are several waveforms available. For example, simple sine waves, periodic shift. So whenever you apply a simple sine wave, you can apply at one specific frequency. On the other hand, if you sweep it across the frequencies, and you can, here we do have the option of peak hold. You can hold the peak for the specified duration, and you can create the envelope. Your sweep will give us a wonderful frequency response as well. And on the other hand, we can even well have the single input, single output response, or you can have the multiple input, multi output response as well. And also periodic shift is why I do want to, let's say, start with one frequency and end at it has series of sine waves with starting from one frequency to ending to whatever the frequency you have selected. So it has the same amplitude of vibration, but different frequencies. Something like this. If I draw the same thing in the time domain, it would come out like this, whereas in the frequency domain, it would come out something like this, right? So it will be having the same amplitude, but different frequencies, right? So what are the different actuation techniques that we can afford to have? The different actuation techniques will be the electrostatic actuation, right? And then one can go forward for the piezoelectric actuation. One can go forward for the acoustic excitation, or you can even well go forward for the base excitation, right? For the first and the fundamental thing, now let us go into the electrostatic actuation. Now, before that, uh, this was basically now I have applied the signal, right? Now I want to go to the post processing. In the post processing, we can see that what is the frequency response of the structure we can measure. And during the post processing, we need to be careful about the peak picking. Even we do get the peaks like this, the stray peaks, we keep in mind uh, how to identify whether that is a noise or the signal from your structure at all, right? So that should be kept in mind, right? So this is the response from the structure. This was a stray peak. So how do we identify that? We will look into how to look into it. So this is the frequency response we can get out. And even if you take away simple cantilever, for the different modes of vibration of the cantilever, what are the frequency associated with it, we can even well get it out with the help of the ATV, right? So and then I told you about the presentation mode. In the presentation mode, we can, well, in this case, this is a case of a gyroscope. Basically, I defined a series of scan points on the gyro. Now, let me see if this video works. Otherwise, I will take you to my mail. Over there, it is there. This is my hammock suspension. Yes. This is a case of a gyroscope with a hammock suspension. So what happens whenever I'm going to apply a potential between the top and the bottom, then what happens? Then there is an electron, right? Then it starts to vibrate up and down. That is what is expected, right? And on the other hand, we did saw several stray peaks during that measurements. That's what I told you earlier. So how did we identify that was a stray peak? If at all you select that stray peak, see how the response comes out. This is how the response comes out. If at all it is a stray peak, that is basically a noise in the system. Now, I even told you that we can even well do it for the cantilevers as well, right? So look at what are the different modes of vibration of a cantilever. This is the fundamental mode of vibration of a cantilever, wherein we had a cantilever B, measured the response. This is the fundamental mode of vibration. And then this is the second mode is over here. This is the second mode of vibration of the cantilever, whereas this is the third mode of vibration of the cantilever. Similarly, we have it till the fifth mode of vibration of the cantilever. And it is not just that we can measure for the out of plane. We can even well measure it when the structures are going in plane, because in case of gyro, these are basically vibrating in plane, right? You can see that when the structures are vibrating in plane, we can still do the measurements of the structure. And this was the case of the gyro, which is moving in the drive direction. And this was the another case of a gyro with folded beams. You can see the motion on the in plane, right? And when there is a Coriolis force, it will start to vibrate in the sense direction. This was my sense motion. Now, I told you that it's not just the accelerometers, gyros. You can even realize the microphones, right? So look at this. This was the case of a microphone, where in this case we have actuated with the help of two. We've actuated with the help of two probes. So there was an electric field. Then the structure started to vibrate in the up and down motion. That's what you basically saw. There was an electric field. So the beams are undergoing bending. The proof mass is moving up and down in the first mode of vibration. Whereas in the second mode of vibration, see this, the number of spatial harmonics will further increase in the higher modes of vibration of the structure. So I basically now showed you how to identify whether it is really response from the structure or it is a noise. If it is stuck at any one of the points, then you can see that this portion is not moving, the remaining portions are moving, right? Accidentally, this video is not working, no, nothing to worry. And I just showed you that I showed you the videos wherein the gyro motion and all those things, right? So we can even well measure the frequency response of the structures like the gyros whenever the structures are moving in plane. All these structures are again realized by the SOI mount process. This is the Z-axis gyroscope realized by the SOI mount process. This is my drive mode frequency. This is my sense mode frequency. That's what is expected out as well, right? Because this is a completely a symmetric structure. So we indeed get a perfect match between the drive and sense mode frequencies under consideration. And this was the case of a comb drive resonator. The comb drive resonators have plenty of applications, right? It basically has a shuttle mass suspended with the help of set of beams. This is also you can realize it using the SY process very easily. Unlike polymers process, wherein stiction is a major problem, SOI stiction is not at all a problem for you. Usually the yield is quite good in the SOI process. And this LEV is not just used for micro and nano structures. One can even well extend it to the natural systems also. Even to diagnose our ears, you can use it also, right? Here you can see the surgeon who is basically doing the measurements with the help of LTP. And for measuring the response using LEV, first and the fundamental thing is that we need to have the actuation unit or the excitation unit. What are the different excitation units that we can have? Excuse me. So the different excitation techniques what we can have will be, the one is that you can go by the electrostatic excitation, right? Whenever you go by the polymers process, you get a top electrode, bottom electrode. Then you can easily actuate it by electrostatic means, correct? On the other hand, if you do by the SOI process, right? So if you are having a cool ray resonators, absolutely no problem. You can still go by the electrostatic means. But let's say that if I want to realize it for whenever there is up and down motion of the structures, that is, let's say I have the top electrode and I don't have the bottom electrode. So I have this, in case of polymers process, I have this bottom electrode, no problem. Whereas in SY process, what it is? I have the silicon. Now I have basically what? I have a membrane like this, that's all. But now I want to measure the dynamic response of this membrane. But there is no bottom electrode over here. First and the fundamental thing, I need to actuate it somehow. And then the LDV can do the measurements. So how can I actuate? Now the actuation became a question mark. So what did we do was we had an array of cantilever beams that we can see it here, array of cantilever beams of different lengths, and we had designed an acoustic horn. What basically an acoustic horn is? Acoustic horn is basically, it is like you might have seen the horn, and at the base of the horn, there is a speaker, right? And the acoustic horn indeed has several air particles inside it, right? Now, the membrane is here. Now, I'm going to vibrate this at a desired frequency. This indeed will disturb the air molecules. Since the aperture diameter over here is very, very small, now we get a pressurized acoustic waves coming out of this, right? Now, these pressurized acoustic waves will come and fall on the structure, right? Once these pressurized acoustic waves come and fall on the structure starts to vibrate, which we can measure it with the help of MSE or LDV, right? So you can see that for the different beam dimensions, this is what is my FEA results, and this is what is my experimental results with different horns. And you can see both of them are comes out to be very well. Okay? If at all you don't have uh, any of the electrical means, if you can't actuate, don't give up. There are several other actuation techniques available for us. So on the other hand, when I was at IISc, so some person from IIT Kharagpur had approached us for the simple cantilevers and other things, simple cantilevers and even the piezoresistive accelerometers. This was a case of cantilevers of different lengths. What we did was we basically kept it on a micro shaker and we measured the response. And those are all just the bare cantilevers. So we basically kept on the micro shakers and we measured the response. And this is how one can easily measure it with the help of the LDV. Now, if at all you don't have the bottom electrode, now I gave you the recipe of what you can do it. Now, whenever you fabricate the structures, right, there are several post-fabrication effects do come in, do kick in during it. For example, if you are realizing the structures by surface micromachining, the stiction is a major problem. And during the processing, we take it to the elevated temperature, bring it down to the room temperature. During the process, because of the CTE mismatch, even there will be a thermal stresses gets induced, and these are all unwanted residue which comes out of the fabrication. That's why parts of residual stresses, and there may be thickness variation, which I already showed you during the fabrication session, on what will be the variation in the thickness in case of the SOI process itself. And if at all there's a blanket metal on top of the structure, what would happen? Let us see what would happen to each case. What would be the effect of residual stresses? Now we have the gyros over here. Now once we saw the gyros, then we saw that the beams were actually bent and we scratched our head. So we measured the response of the structure. One structure was having a length of 300 micrometers. Other structure was having a length of 400 micrometers. The experimentally obtained resonant frequencies was this, whereas analytically obtained frequencies were this. He said, why is this so much difference between the two? What is making it so much different? So Once we modeled it analytically, but whenever we looked at under the microscope, we saw that beams are actually bent. They were not straight. So as to relieve the residual stresses, the beams got bent. Now we indeed modeled it as a guided cantilever, and we come out with an expression for the frequency of the guided cantilever. This is basically comes out as the square root of potential energy divided by the kinetic energy. This comes out from the strain energy in the beam, and this is for second term over here, comes out from the built-in residual stresses, and this is from the mass of the beam, this is the mass of the plate. So if you take up y of x to be this and substitute into this, you will come up with the expression for omega squared to be this, right? Now, in the case, I have beams of two different lengths. I have two different frequencies. Now, if you take up this, let's say one is LA, other one is LB, and for let's say we have FA for LA and FB for LB, then you can evaluate here. We have two equations and two unknowns with us. So let us assume that E and sigma, I don't know. Now let us evaluate E and sigma from this. One is FA, other one is my FB. Just substitute back and evaluate E and sigma. If you do that, you can see that if you back calculate, you can basically get 130 gigapascals and 77 megapascals under consideration. Same thing, you can even well do it through your numerical software also. This is one is without stresses, and if there are pre-stresses are there in the structure, then what happens to the natural frequency of the system that you can see, right? And if at all there is a thickness variation or the metal coating, what would happen? This I already showed you that whenever there is a case of an cantilever beam, right? For different modes of vibration, we can extract it out with the help of LDV. I showed you the mode shapes as well. And for different modes of vibration, these were my natural frequencies associated with it, right? Now, this was done by polymers process earlier. For this, the cantilever, in case of polymers, the typical thickness will be around 2 microns, and the width was this, length was this. This was taken from the geometry, right? But this frequency for the cantilever is basically given by C by 2 pi times square root of EI by rho L to the power of 4. So for C, for different modes of vibrations of this, from first mode to fifth mode is given by this. And if you evaluate it analytically, this is what I get. But experimentally, if I had evaluated, look at this. This is what is my experimental values. The same thing I had tabulated here. The experimental values are over here. My analytical values are way ahead of the experimental values. Now, if you divide one by the other, the analytical values by the experimental means, we can see that for every mode, it had changed by a factor of 2.2 always. So we said, why there is a constant shift of 2.2? What is the reason behind it? So then, once we looked into it carefully, then we saw that on top of this polysilicon, there was actually a gold layer which was sitting there, right? Just like how you had a blanket metal layer, right? And also a pad metal layer. If you by chance you keep a pad metal layer on top of your silicon in this your process, then also you will come across the same thing, right? So then instead of becoming like a simple beam, now it became like a composite beam. Now for the composite beam, you need to evaluate the effective flexural rigidity and the effective density under consideration. And then you have to do that, and then you come back and evaluate. Then this is what it comes out for the ideal conditions, right? For the by considering it as a composite beam, by considering it to be a mean value of this and gold thickness of this, I will get a variation of 15%. On the other hand, if you take up a lower bound, I will take up a I'll get an error of 5%. Upper bound gives us a much more error of around 21%. Okay. So this is how one can easily do the measurements with the LDV, and you can evaluate all the mechanical properties of the structure, right? Put the piece here. Yes, any doubts till now, please? Please feel free. So you can always type out, please. And there are even other techniques for evaluating. The other one is by making use of position sensing detector. The position sensing detector is like an array of photo detectors, right? So let me explain you the position sensing detector. Right? The position sensing detector, or a PSD, is an array of photodetectors. Right? In case of LDV, the problem what we see is that it is very good. It even gives to a picometer resolution, but it wants surface to be reflective. Right? If at all your surface is not reflective, then you can't do measurements with LDV. And at the same time, with your cases with silicon-based structures, absolutely no problem. LDV can do the job, right? But on the other hand, if you have the structures with the soft lithography process with PDMS and even many of the biological samples, the LDV is a troublesome, right? So what we can do is that we can actually devise our own instrument wherein we can make use of position sensing detector. The position sensing detector, the working principle is quite simple. The position sensing detector basically consists of an array of photodetectors. So let us say that this is my structure, this is my cantilever, this is my cantilever. Now, first and the fundamental thing is that I will use a laser source. I have a laser source and I will shine the laser light on the cantilever, right? And when the cantilever undergoes deflection, then what happens? It will come and it will fall on the PSD or the position sensing detector. What exactly is a position sensing detector consists of? A position sensing detector basically consists of an array of photo detectors. An array of photo detectors, a three-dimensional array of photo detectors, a two-dimensional array, sorry, not a three-dimensional array. So initially, when the structure is at rest, we need to ensure that we do the zero setting so that it will come and fall exactly at the center. Now, when the cantilever will undergo deflection, then what happens? Laser will fall at this position and it will come and fall on some other position on the PSD, right? And this PSD is further connected to PSD electronics, which further converts this PSD electronics will convert whatsoever is the position wherever it has fallen into the displacement of the structure. So this PSD electronics will come in two things. One is AC operating point and the other one is a DC operating point circuits. The DC operating point circuits will be used for measuring the static displacements of the structure. Whenever you want to measure the static displacement, you can use the DC measurement point. Whenever you want to measure the dynamic response, you can go forward for the AC measurement. AC operating point, right? So this is basic working principle of the position sensing detector. Now, in case of this, right, if you take up any of the samples, which are in case of many of the microfluidic applications, we will realize the structures with PDMS, right? Let us say the cantilever is realized using the soft lithography and PDMS, and I want to measure the response. So if at all laser falls on the PDMS, then what happens? It will actually refract. It will not reflect, right? If at all you want to make it to reflective, then I have to coat with either gold or some other or reflective material on top of it, right? Then it indeed will change the properties of the material completely. So it will, rather than just like how I showed you for a simple cantilever, instead of becoming like a simple structure, now it became like a composite beam. Again, this also becomes like a composite beam, right? So instead of having so, what we can do is that we can have a laser source at the top and we can keep the PSD at the bottom, right? So PSD will be very, very handy than your LDV, right? So in this case, but you need to be very careful while handling it. That's the main thing. Okay, wherein we can keep the laser source at the top and we need to keep the PSD at the bottom. And whenever the structure undergoes bending, then it will come and fall on the different position on the PSD. That will basically give us the deflection out. And indeed, the atomic force microscope, majority of you might have known it by the name AFM, makes use of this PSD for measuring the deflections of the cantilever. So what exactly does an atomic force microscope consist of? An atomic force microscope basically consists of a cantilever beam, and this cantilever beam indeed will traverse on any sample, right? Any sample, and we will basically have a laser source, and the deflected beam will basically come and fall on the PSD, position sensing detector. When the AFM will come, what? Let us say it has a topology like this. When the AFM cantilever comes in contact with this, then what happens? Because the intermolecular interaction, then it will indeed will experience a force, right? So the cantilever will undergo deflection. So this deflections will indeed can give us, one is that you can get the topology data. Other one, it can even well give us the force measurement data, right? Well, you can get the topology measurements, you can get the force measurements, and I told you about the lithography process and all those things, right? Now, in case of AFM, you can even well do the lithography using AFM also. That is what we even call the electrolithography. That's what we call the electrolithography. As we know that in case of AFM, we have a sharp tip, right? Now, we have a substrate now. We have a substrate. Now you apply a potential between this AFM and the substrate. Then what happens? With this, we will get a localized heating at this point. There you do get huge joule heating at this position, because what happens? The J will be equals to I by A. A will be very, very small. So this will get heated up, and electromigration, you might have seen majority of the electrical circuit, it's a detrimental to the performance. So indeed the electromigration will happen, and it will start to eat away the material from the substrate. And you can even well pattern plenty whatever shapes you want on the structure. For example, you can even pattern the structures like boom, whatever shape you wish, you can pattern it with the help of AFM, right? Whereas patterning the shapes like ohm and other things is very, very tough using any of the conventional micro or nanolithography process under consideration. So you can even well do the electrolithography using the atomic force microscopy. Now it is not just the atomic force microscopy on this. There are plenty of other characterization techniques, such as plenty of other characterization techniques like acoustic microscopy, wherein we can measure the, or let's say, even if you have the packaged devices without even opening the device, just like how the when the ultrasound passes on our body, it will give us all the images, right? The scanning acoustic microscope even tell us what are the elastic moduli of the each and individual parts within the complete assembly. You can extract it out with the help of a scanning acoustic microscope. That is what he basically calls a SAM, right? And on the other hand, the MEMS structures are not just the mechanical structures, they are indeed the electrical structure. Electrical devices are also there. And I indeed covered quite details about the pull-in also, right? So as to measure the electrical properties, you can make use of DC probe station. We can make use of the DC probe station to measure the electrical properties of the micro or nano structures. With the DC probe station, you can evaluate the IV measurements, CV measurements. Even you can come connect it to an impedance analyzer, and you can do the complete spectroscopy. Quite lot can be done with the help of the DC probe station, and you can evaluate the pull-in voltage, and plenty of things can be done out of there as well. And also, of course, there are plenty of things which are there in terms of the optics also, or you can even do with acoustic microscope is one, and you can even do the things with the scanning electron microscope and the scanning tunneling microscope. The plenty of other things are also here. Okay. Okay. I will stop here. I think Pradeep, would you like to take up on the A layout? Any doubts till now, please? Now, Pradeep is my PhD student. He will just give you the brief about how to use the K layout. K layout is an open access tool for all of you. All of you can use it. Okay. He will just give one sample example on what exactly are the capabilities of the K layout and what you can do with it. I told you during the fabrication about the different layers and other things. He will just show you a sample of. Okay, over to Pradeep.
Okay, thank you, sir. I'm sharing my screen, sir. Is it visible?
Yes, it is visible to me. Please.
Okay, thank you.
Yes.
Okay, just a second. Good morning, good afternoon, and good evening, everyone. Well, my name is Pradeep Shukla. I am the research scholar at the Department of Mechanical Engineering. Today, I am here to present some basic idea about the different kinds of the editors layout editors and viewer softwares. First, we are going through the MEMS fabrication course, so we have basic idea about that, what is the MEMS and all. We have already discussed all the things, but just I am trying to connect these things with our why we are using these kinds of softwares. Okay, so MEMS is what, that is the device in micron size. As, and limitations of the device which is in micron size. The main thing is that we have some conventional machining processes. Machines are there by using which we cannot able to, just a minute, we cannot able to just a minute, sir. We are not able to produce the device in micron size because the main thing is that we have some conventional machines like EDM, ECM, and CNC milling tools. These are not capable to produce the structures and produce the dimension in the micron range. Another limitation is what? That is the use of the in the microelectrical mechanical systems. We are using silicon as a substrate. So the main thing is that the silicon is highly crystalline materials, and the silicon is also a brittle material. And if we are using these kinds of ECM, EDM, CNC machine tools, and if some variation in the forces are there, due to this, the device get break. So these are the basic limitations due to which we are not go with the conventional machines. So to produce the MEMS devices, we required some photolithography type methods by using which we can create the microstructures and the layers in the micron size so that we can create devices. Okay, so we have already, Sarah has already told about the lithography. By using the in a lithography, that is comes from the Greek word litho, which means the stone, and graphia, which means to write. So photolithography is basically the process of producing pattern on the semiconductor crystals for use as a integrated circuits. So in the photography, the main thing which is majorly useful, that is the photo mask. Basically photo mask is the main key which is allow the allow the photo mask is basically uh, allow the laser to hit the substrate and remove the materials. So photo mask is served as the blueprint of the defining MEMS structure. It is almost the similar like the MEMS structure what we want to produce. These are the examples over there by which we can see that the in the this we can see that this is the first layer where we have used this kind of structure. In the second layer we have created another structure like this, and in the third layer we have some different kinds of structure like this. So by using different kinds of the photo mask, and we can create a different layer structure which is useful for the photolithography method and useful for the creating the MEMS structures. Okay. So conventional software for creating the structures and geometries are AutoCAD, SolidWorks, and other different kinds of softwares are available, which is useful for creating the simple geometries. But the thing is that by using these softwares, we are not able to create the GDS file format, which is the map, important for the photo mask creation. So these are the limitations. To overcome these limitations, there are the different kinds of new layout design softwares are prepared, especially in which are able to produce the GDS and OSS software, which is compatible with the photo mask fabrication equipment. So layout design software is mainly, these are the used for the blueprint creation, and it is translating the design into the fabrication. Second thing is the layout design software, where the multi-layer design and alignment of these these layers can be easily possible with the help of these design softwares. Generally, in the fabrication of the lithography, we can have already seen that the layer by layer fabrication are there. That means the whole fabrication is divided into the different kinds of the layers, so that these softwares are very compatible and very useful for creating the multi-layer design and alignment of the these designs. Next thing is what the precision and accuracy. Generally, these design softwares having the tools like the grid and scaling tools, which are very useful for creating the very precision and very accurate design. Another main important thing of using the layout editor and designing software, they have inbuilt error checking and verification tool, which is useful for the checking and validating and verification of the developed design. In this tools, design rule checking methods are there, by using which we can check before going for the fabrication. We can check our design it is suitable for the fabrication or not, and it is also having ability to integrate with the different softwares and to do the simulations and all, and connect with the simulation softwares. And the main advantage is that the previous limitations like AutoCAD and SolidWorks are not able to create the GDS and OSS format which is compatible with the photo mask fabrication equipment. So these layout design softwares are suitable and especially made for the photo mask fabrication equipment which require the GDS and OSS softwares. Another thing is that it is suitable for the error checking and verification. So this software is quite helpful to create the fast design as well as reduce the hit and trial method, so that it increase the cost and time efficiency. Next thing is what the different kinds of the layout design softwares. These are some softwares like K Layout, Kelvin, Tanner L Edit. These are the different kinds of softwares. Many more are there. I have just written these three. Many more softwares are there by using which we can create the multi-layer structures. Then what is K Layout? K Layout is basically an open source layout editor and viewer software which is used for the MEMS and IC design. The key features of the K layout is a multi-layers. It is a multi-layer support software in which we can create the multi-layer structures, and it is support these things. Another thing is that it is suitable for creating the GDS and OSS file handling. They have already design rule checking inbuilt in it, that so that we can check our design it is suitable for the fabrication or not. They have also Python scripting for the customization of designing is available in this software. And the main thing is that the K layout is accessible and flexible and powerful for the industry standard designs. And it is also a open source software, so we can easily get it and use it. Next thing is what that is the demonstration of the K layout. We can directly go for the K layout. We can directly Google search, and it is an open form software, so we can easily download it and install it. By using this, we can go it here and get K layout, and from here we can download it as per our suitable things. So for Windows 32 and 64-bit, we can directly download from here and install it. I have already downloaded it and installed it, so I can directly go through and go to that point. You can go by this method and you can install that particular software. And I'm going to the K layout editor. Just a minute. Sorry. This is the our key layout software. For start the design, we have to open the layout window. So we can go to the file option, and here in the file option we have the new layout. We can select it, and by selecting this we can see that window. In that, we there are some things, and database unit and initial window size. So we can select the initial window size what we want from here only. So this is here 2 microns. I am going with this 2 microns. Just okay is now after okay, this now we have find that this is open that this three sections are there. One is the cell, another is library and layer. And this center portion is the area where we are creating our geometries and our structures. Okay, so I'm starting with the these different kinds of the uh, different points are there, like select, move, ruler, addition, subtraction, polygon, box. These we can use these commands to create the different kinds of structures. Some these command box are already there: file, edit, view and display and all. So before starting that, I'm just selecting first a box, the very simple things. Okay, so before starting we have to select the layer. If we haven't select the layer, then we are not able to create the geometry over there. Layer is just like the we can say that the metallic area where we want to create that structure. So first we have to select the layer. Okay, so we can go to the edit option. In the edit option we have some different kinds of options are there. First we go to the layer and we select the new layer. And when we are selecting the new layer, we have opened this window where we can give the name for that layer. Suppose I am saying that this is our layer A. Now after creating that layer, we can see that this is our layer. Then we have to select this layer, and after selection of this layer we can create something. Suppose we can go with the different kinds of geometry. First I am selecting a box. We can go, and I am just uh, creating by freehand. So first what we have to do, we have to just select the layer here. And when we are selecting this layer, if this thing is highlighted, you can see that the right corner there is an option for the layers. And if we are selecting the multiple layers, we can easily see from here that how many layers are there and how we are working. So this is the layer 1. The name of that layer 1 is A, and we have selected that. It is already showing the highlighted portion is indicating that we are working on the layer 1. So first we have selected the layer 1, and in this layer we have taken the box. Like this is our box, and this is the box type geometry. And we can use this box of type geometry for the our creation of the different kinds of the structures and designs over there. We have some different kinds of options there. First thing is that is the select. By using this select option we can select this particular geometry what is available in this layer. And another thing is, another option is move. By using this we can move this geometry from anywhere in our layout. Another option is that these are the basic options uh, which is required for designing and developing the geometry for the mask. This is the third one is the ruler. by using this ruler, we can, if we selected that ruler, we can just check the dimension and of the geometry, and we can measure the things in any directions. Okay, if we go with the shift, then it will move in the orthogonal direction only. Suppose we want to measure the dimension between these two things, and if we want to measure these two things, we can just select it, these 2 points, and we can easily get the dimension of these are all the dimension in the microns. By using the rulers, we can go for the check what is the dimension of this particular structure. Again, after that, they have some different kinds of other options. That is the polygon. By using the polygon, we can create the structures. After pressing the button, we can go for the another lines, and by using this we can create any kind of substructure. And if we double click, then you can see that we can create this structure. So by using polygon, we can create the different kinds of structure. Okay, after that, we have some text arrangement, some path. The structure is also there. If we want to create some micro channels, some paths, so we can create these paths by using this path options. If we can see that, we can go with this path option, and we can easily able to create the path in the geometry. We can minimize it. Also scroll up and scroll down by using the mouse button. So you can see that one thing, we can adjust the path width by using this corner. We have the option to adjust the width. We can adjust the width by using this option. It is suppose I am selecting 2. Now you can see that if we are going for this, then you can see that if we are selecting this path, we can create the microstructures, micro path and other things. And even if we are continuing, we can also create the different likes structure. You can see that width is too high. This is 2 micron. That's why you can see that we can create the microstructures like this. Suppose I am reducing it to the 0.5, and now you can see that the width is reduced, and we can control this according to our need. Okay, so we can just select all and delete it. And another options are also available there for the modification and modification of the designs as per our requirement. Like this is our add and merge option. By using the merge option, suppose if we want to merge two geometries, we can directly, we have already prepared one geometry, and after that we can create the another geometry. If we have used the merge option, these two geometries directly get merged. We can again see that if we have the merge option selected, then we can go to the box. If I am creating the box over here, then you can clearly see that these two boxes can easily merge with each others. Okay, another option for editing and modifying our geometry is erase. By using the erase, we can remove something from our geometry. Like that, if we are selecting the box, and this is our initial geometry, and if we are creating a box inside that geometry, and we select that, now you can see that the portion which is covered with the box from the previous geometry is get erased. You can see that one line is there. It is not the defect over there. Generally, what is happening there, the K layout is mainly deal with the GDS file format, and these GDS file is mainly work with the vertices. That's why it always act as the closed geometry, so that one line is showing here which is connecting this with this hollow section. So that's why that extra line is there which is connecting these things, these hollow structure with this previous structure. Okay, another option is there, the mask. By using the mask, we can remove the material over here. Suppose I am taking the mask option. Okay, before mask, I am taking the extra box. Suppose this is our box. By using this, we can go the mask option. We have selected another box. Now you can see that mask option will have to remove the other portion of the geometry. If you want to remove the other portion of the geometry, what we can do, we can go with the mask operation, and in the mask uh, operation, we can see that the except the mask which is covered with the mask, we can remove it with the help of this mask. And another one is the difference. If we can create the two different boxes, suppose this is our box 1 and this is our box 2, and suppose I merge these two boxes. Now if we go for the difference, I have selected the box, and if we are using the difference, now you can see that this portion get removed from the previous geometry. So these are the uh, basic tools which we can use for the creating the geometry and editing the geometry. We have also some different kinds of tools available. Suppose if we can go to the edit, in edit we can go to the selection, and in selection we have some different kinds of other editing options are there. Just flip horizontally, flip vertically, rotate clockwise. Suppose if you are selecting the flip horizontally, now you can see that if we selected this and we go for the selection option, here we can choose the flip horizontally. Now you can see that that geometry is flipped with the horizontal. These uh, all the tools are very helpful for creating the micro designing and microstructures. So again, if we go for the selection, you can see that there is another option, that is the flip vertically. We move to the move, if we select this portion and we go for the vertical flip, you can see that the whole geometry get flipped by in the vertical direction. Another thing, if we go to the layer selection, go for the rotate in clockwise direction. So we have already, first we have to select the geometry. I have selected this geometry. Then we go for the edit option, selection option. In the selection option, again we have another option, that is the rotate in clockwise direction. By using this, we can rotate the whole geometry with the 90-degree in the clockwise direction. Another option is what? That is the selection, rotate in the counterclockwise direction. If we apply this, we can rotate the whole geometry in the counterclockwise direction. And another main options is rotation by angle. We can also provide the angle. By using the angle, we can rotate in a particular angle. Suppose I am selecting this one, I am selecting the angle like 45-degree, and this we can go through that. Now you can see that this whole structure which is selected previously, it tilt in the angle of the 45-degree. Another options, there are so many options are there. This is the scale options is also there. By using this scale, we can uh, use the scaling factor to reduce and enlarge the size of our structure. Suppose I am selecting 0.5 scale factor. So after selecting the 0.5 scale factor, you can see that if we select this, the whole geometry get reduced by 0.5 scale. So by using these kinds of the another options, we have moved to option to particular look. If we want to move our structure in a particular location, so by using the move to option, we can just give the uh, location of the x and y reference, and then on the basis of that, this particular structure move to on that particular point what we have given in the move to option. Another is move by option. Move by option is used for moving our particular structure from their reference point to the certain position. Suppose if we want to move in the x direction with the 10 mm, so what we can do that we can just give the 10 mm 10 microns move by direction, so that if we use this particular option, that whole structure will move 10 micron in the direction of the x. And another option is also there, make an array. By using this we can create the array. Suppose if we are selecting this, we can go for the selection option, we can go for the make an array, and it is of in this we can see that here it is asking for the number of row and column. We can provide the number of row and column for the for the array. Suppose I am selecting 3 rows, 3 columns, and 2 rows. And by using this we can go for that. Now you can see that the structure we can create the array of this structure. The thing is that we have to also mention that the gap between these two structure, if we can control the gap between these two structure, if we increase the gap between these two structure, it will move in vertical direction, and put structures get in the different we can control the space between the arrays. Another option is there, tab alignment distribution round corner. Suppose if we want to create the round corner, we have selected this. Suppose this is our uh, box structure. I have selected this box structure, and we go for the edit option. And in the edit option, we go for the selection. Now you can see that in this section there is a round corner option. By using this round corner option, it is asking for the initial radius. Suppose I am selecting this initial radius as a 1 micron, then you can see that. Okay, wait, edit, go for the selection, and where is this particular option, distribution round corner. In the round corner, we if I am selecting the value of 0.0002 micron, then you can see that okay, number segment is not more than 10, so I am selecting 0.2. So by using, it is not working right now, so by using this we can convert this box into the by using this option we can round our corners with the different initial diameters and radius what we have option. We can give the initial radius. By using this we can round these corners. Okay, so by using these kinds of different tools we can modify and adjust our geometry, and we can create the microstructure. The main advantage of this tool, we can create the multi-layer structure. And suppose if I am selecting all and deleting all these things, and now we are going for the layer structure, how we can layer the multiple structures. So this is the layer one. We have already seen that in this right corner, we can create the multiple layers and over which we can create the multiple structures. So in this section, initially we have seen that we have the one layer, that is the layer one in which we are working. Suppose I am creating the box like this. This is the box one. It is here in the layer one, and suppose I am taking the difference option. We have again taking the box one, and we can take this section here. So we have created that kind of geometry in the box one. uh, we have initially created the box one and over another box, and we can create we have taken the difference between these two so that we can remove the material from this portion. And if we want to create the multi-layer structure, that means we have to create another layer over the that particular layer, and we can create the another structure over this layer. So what we can do that, we can go for the edit option, and in here in the edit option we have the options for the layers. So by using this layer option we can clearly see that there are multiple options, like we can create the new layers, clear the layers, delete the layers, we can also copy these layers and edit the layer specification. We can also change the specification by using this particular option. Boolean operation, we can if you want to uh, do the boolean between the layers, we can use this operation. Merge operation and size, we can vary and change the size of the layers. So here we want to do the experiment, sorry, here we want to create the multi layer structure. So what we can do that, first I will remove this, delete. We can go to the edit option. In the edit we can go for the layer and go in the new layer structure. So if we selected this new layer option, then you can see that this is the again one window is there. In this window we can mention that this is our layer 2, and we can give the name as according to the metal and another specific thing what we want to name that particular layer. So here I am selecting B as a layer name B, layer name as a B, and just click the OK. Now you can see that in the top right corner, we can see that now initially we have one layer, that is A1. Now you can see that this is the layer B2 is there. By using these two layers, if suppose I want to create another layer, we can another go for the edit option, and in the layers we can go for the another new layers. And in this another, I am creating the naming that 3, and give the name for the layer 3 is the C, and now this, and so on. By using this option in the edit and layer, we can create the multiple layers, and we can clearly see that how many layers we are working. You can clearly see at the top right corner of there, you can see that the highlighted portion is the in one, so that it is indicating that we are working in the layer 1. Suppose we want to work in the layer 2, what we can do, we can go for the layer 2. When we select the layer 2, okay, and it is now we can clearly see that this portion is highlighted, so that we can now identify that layer 2 is active. And in the layer 2, what we can do that, we can create something. Suppose we want to create another geometry over there. So you can clearly see that we can also arrange the uh, colors of the layers. So we can give the different kinds of layers. So layer color. So we can easily identify that which one is the layer 1 and which one is the layer 2 and so on. Suppose we am selecting the blue one. So you can clearly see that now the structure in the layer 2 is this. Again, suppose I want to create another box over there, and this is the box 2, and now you can see that we have opened the option difference. That's why the second box portion from the box 1 and get removed and get difference over there. So we can create the geometry like this in the layer 2. And on the basis of that, if suppose we can also give the another portion, another area, in another area. Suppose if we want to create something from this portion, we can use different like merge and all. Suppose I want to merge these two things, we can create like this. So by using the layers, you can clearly see that the whole whatever we are creating the structure, it is in the layer 2. It is not affecting the structure of the layer 1. We can't use these kinds of operation like merge, erase, mask, and difference option between these two different layers. So these all operation can only we can perform in the same layers. So by using this, we can create the different kinds of structure. Suppose I am selecting the select option. I have selected this, and this, and remove this. Okay, so this is our layer 1, this is our layer 2. So we have selected layer 1 also. That's why the whole portion is from the layer 1 is also removed. So we can create it once again. What we can do, we can go for the layer 1, and in the layer 1, now this is the layer 1 is selected. We can create this box over here, and we can go for the layer, another box over there. Suppose I have taken this box over there. Okay, this is merge option is there. That's why it does not make the difference. Now I have taken this another box over here, and we have taken the difference between these two. And now we go for the layer 2, and we have taken the box again. And suppose I want to create something here. This is another geometry. This is another. So we can take the different patterns by using this and different box options. Suppose if we want to create this one, and suppose I want to merge all things, we have create this options, and again we create this option. So whatever we have created, that is in the layer 2. If we want to create some some structures in the layer 3, so what we can do, that we can just go for the layer 3, and once we can select the layer 3, and we can create the another structure in the different layer. So here now when we go for the layer 3, you can clearly see in the top right side in the layer options there is the layer 3. It is highlighted. That means the layer 3 is active. Now we can do the work in the layer 3 option. So if we go for the box, another box, and suppose I am creating something like this, and the color of the layer 3 is almost similar with the layer 2. So what we can do, that we can change our layer color. I'm selecting black. Now we can clearly see that the whole red portion is developed in the layer 1, the another portion, blue portion, is developed in the layer 2, and another portion is layer 3, which is developed with the color 3, color black. So suppose if we want to create something in the layer 3, I have taken the difference option, selected the box over here, and if we want to this, now you can see that in the layer 3 this particular type of structure we can create. And suppose we want to create another box over here, and again we want to take the difference. We can go for the merge option. Now you can see that this. So you can see that in the different layers we can create the different structures, and after that we can align it and we can also go for the DRC checking, so that we can check that whether it is compatible for the fabrication or not. So, and this is the basic idea about the key layout. We can also go for the multiple layers, like if we want to go for the layer 3, we can again select the new layers here, and we can existing layer 3. Okay, so we can go for the new layers. Here we have to mention that this is our layer 4, and the name of that particular layer is D. And by using this and so on, by using this option, we can create the multiple layers what we want to create. I'm just trying to create an one structure over there, which is present over here. So first I go for the layers 1, and I have selected this portion. Okay, first select this. We can go for the selection here. We selected this, we can delete this portion. So by deleting these kinds of things, we can remove the structures, and by using this layer kind of things, this multiple layer structures allowed to create the different structure, and we can create the mask with the multi-layer structures. So suppose I want to create a new structure. I have selected the layer A1. Okay, this is layer A1 selected. Now we can create this. And in this layer, we are going to create some different structures. Like suppose I am taking the another box and taking the difference between these two. This, another this. And if we go for the layer B, we can create the box from here. These different kinds of structures we can create by using the layer options. So by using the multi-layer options, we can create the different structures which is useful for the lithography. And this is all about the basics of the K layout. We have some another different options. And by using this, we can create the different kinds of structures which will be useful for the photolithography. So this is all about the basics of the K layout. We can save these files by using the save options. We can create the names. We have the different kinds of all file formats. We can select this one, whatever we want. We can create the name of K layout, and we can save it. And we have another option. We can import also the different files from different softwares for the new project and all. By using this K layout, we can create the we using the K layout, we can create the layer by layer fabrication, and by using this, we can use the multi-layer design and alignment options, which is very helpful for creating the photo mask for the photolithography techniques, and by using which we can use it in the photolithography options, and we can create the different microstructures and micro devices. We can fabricate it. So this is all about the basics of the K layout. Sir, this is done from my side.
Okay, thank you, Pradeep.
Thank you, sir.
Yes, any questions from anyone, please let us know. Okay. Will there be a template provided for the startup? Yes, there is a template, but they don't give it especially for the key layout. They usually make use of the mental graphics. But you can export that to GDS file and you can use it in key layout. Yes, any other questions, please?
Okay, so if there are no more questions, I think we are close to the finishing time. I would like to thank Professor Venkatesh and Mr. Pradeep for the insightful comments and details on MEMS microfabrication, about process flow and characterization, and also about the designing using the K-layout software. Thank you very much for your presentations and for your introduction to this technology. And this is the last seminar. So after this, we will continue with the fabrication process and you all will receive more information and details about it. And in case you have any questions, please feel free to contact Professor Venkatesh, Mr. Schumann, Acharya, and Pradeep, and they will be, I'm sure they will be happy to help you with this. So thank you very much to everyone. Have a nice weekend and enjoy the coming holidays.
Okay, thank you. Thank you, Carlos.
Thank
Thank you all. Enjoy the holidays.
Mhm.
Bye.
Bye bye.
Bye.
Thank you.